Center for Astronomy and Astrophysics. We are celebrating our 34th Foundation Day, and it's been a great journey being here and also interacting with the excellent Pune audiences during our public events which happen here. We are very happy also to welcome you back to this auditorium, this illustrious auditorium named after Professor Subramaniam Chandrasekhar, who himself inaugurated this. And you are again able to attend in-person talks and other events in this great location. So again, welcome you all. We are now ready to host the excellent lecture today by our eminent speaker. And we have audiences here and online, so I also would like to welcome you on our YouTube channel. So I would first request our director, Professor Shomak Raichaudhuri, to introduce the speaker to you all. Sir.
I'm very happy to see everybody here. Good afternoon, and welcome to the 34th IUCAA Foundation lecture. We have lots of lectures all through the year in various locations, including this auditorium. But this is a very special lecture. This happens once a year. Our Foundation Day celebrations started yesterday. Actually, today is the Foundation Day, the day in 1988 when IUCAA was founded. And we started with a cultural program here in this auditorium, absolutely fantastic 3 hours. And then we had the annual dinner, and then now it ends with this great event, which is our event that we look forward to all year. And if you are a regular here, you would know that we've had some really, really memorable Foundation Day talks in recent years. Many of them, of course, all of them in the last few years have been they're on YouTube, on our channel. You can follow them. Also, it is great to come back to this auditorium. It's been closed for 3 years due to renovation and the lockdown, etc. A lot of things are new. The projection system is new. The audio is new, and people who have followed this place for a long time would know that there have been lots of problems with our various systems, and now it's back online. And I hope this will be you will come back here for more and more talks. This is also my last Foundation Day celebrations as director of IUCAA, so this is very special for me, and to see all of you here in this auditorium. Thank you very much for coming. Dr. Satishchandra Ogale, I'm very happy that this occasion, today on the 34th Foundation Day, he agreed to be our orator, our speaker. Many of you have come here because you know Professor Ogale. He needs no introduction. He's quite an icon in Pune. Professor Ogale is now a director of the Research Institute for Sustainable Energy, RISE, which is part of the TCG CREST Chatterjee Group set of institutes in Kolkata. But of course, he's also the emeritus professor at the Department of Physics and Center for Energy Science, which he established in IISER Pune. Before that, he was a faculty in Pune University for many years. He was telling me he was associate professor at Pune University when IUCAA was founded. So all the people who founded IUCAA, of course, interacted with the physics department very closely at that time. And Professor Ogale knows us from the very beginning. And this was several years before I joined IUCAA. And before that, he was at the University of Maryland for 10 years. And then in NCL, Pune, for a while. So he's been around in Pune for a long time, but he has connections across the world. Publications-wise, almost everybody knows some of Professor Ogale's seminal publications. He's more than 500 publications. His Google Scholar H-index is 85, with more than 35,000 citations. So that just tells you the kind of profile he has. Supervised over 65 PhD students, and then and he has 9 US patents based on the work he did after returning to India. So and some of them, I suppose, might feature in today's lecture. He has many, many national awards and recognitions, including the INSA Young Scientist Medal. Just told me this morning that Professor Saikia, who's a member of IUCAA, and he received the INSA Young Scientist in the same year. So you see, you have old friends in every corner. And the BM Prize, C.V. Raman Prize, Raja Ramanna Fellowship, Ramanujan Fellowship, all kinds of very, very prestigious awards. Professor Ogale is an elected fellow of the Indian Academy of Sciences, National Academy of Science, and the Maharashtra Academy of Science. So it's our great honor to welcome him on stage to give the Foundation Day lecture.
May I request everyone to mute their mobile devices if they have not done it yet? Thank you. Sorry.
Hello, can you hear me? Okay, all right. Yeah. Yeah. You put this off, right? Yeah. Okay, thank you, Professor Shomak Roy Chaudhary. He is one friend now. After a little while, we had interacted, and we had interacted in the past for some time, but only recently I had arranged a conference through my startup called SNT Digital. Through that, I had a very interesting conference on higher education, research, and innovation, and he was one of the speakers. Thank you very much for the kind words of introduction, and it is an honor to be giving a talk in this forum, especially on the Foundation Day. Okay, as you rightly said, I was a young associate professor in '88 in Pune University when all this action was going on, and Professor Narlikar, Professor Dadich, they were constantly visiting here for all those planning and management and so on. And I have known almost all directors here, Professor Kembavi, then Sanjeev Dhurandhar was there, and a number of other people I have known for many, many years as friends, actually. So it is always a pleasure. I've been coming here occasionally, but then more recently in the last few years, because of one reason or the other, I had not come. So this is a wonderful opportunity to be here. And thank you very much for this opportunity and an honor. So it is important that he's the one we must sort of acknowledge, who has been the visionary who has established this institute. And I remember when I was in high school, he had just returned from UK, and there was a lecture which my father took me as a senior high school student, and that was in the SP College ground. Can you imagine? And there was a pendal, like a politician, giving a talk. And we were all, the whole SP College ground where we used to go to play cricket. It was a central podium, and he gave a talk. And that time everybody was so charged that one Indian scientist has come back, and he has a new theory about everything and things like that. And he talked about Big Bang versus steady state theory and so on. And we all feel elated that an Indian, and he was our role model, that somebody to look up to, and he was so young at that time when it was his first lecture. And SP College ground, I had been there for Atal Bihari Vajpayee's talk later, or Indira Gandhi's talk, but Jan Narlikar gave a talk on that ground, and I still have a vivid memory of sitting there as a student and listening to what he was doing. And when he came here started this IUCAA sort of plan and program, he visited several times. And in fact, he was also teaching in the physics department. There was a TIFR Pune University exchange program. He was there. Professor Udgaonkar was there. Number of other people came and taught and so on. So this relationship between TIFR and Pune University was cemented through these particular earlier interactions. And I think it is a pleasure that so many young people, generally, astrophysics is the people principle which everybody loves, right when you are in the school and outside and going to the university, if you ask everybody, what do you want to do? What subject do you love? Everybody says, I love astrophysics, and slowly they divert and do other things. But all of us are too excited, and an institute in Pune of this kind of caliber and proportion and strength is something which is a blessing for our city as well and the whole region, okay? Now, the topic that I have taken today is something that I have been sort of thinking about and working for the last about 10 to 12 years. I was earlier in a different field, in the field of high temperature superconductivity, magnetisms, metal oxides, multiferroids, things like that. But when I returned from US in around 2006, I decided that in this phase of career, I need to do something which has some connection with society, and if there is something where one could do which is of relevance to society. See, all of us do everything which eventually is of relevance to society. You take astrophysics, material science, everything is important. But I thought that there are some direct connections, some work which is applied science of sorts can lead to some direct connections where we can see its effects in really in the immediate future. That way, entire science actually sort of leads us to very big advances, but there is something on the shorter term can we see where the effects of our research can be seen. So that was my idea of going into this particular zone of energy. So the topic that I've chosen today is building sustainable future, complex problems in search of pragmatic innovations. So this word pragmatic innovations, I actually coined for myself, when Shomak actually wrote to me, would you give the talk? But then I went on to Google, I said, is it existing somewhere? But there are one or two websites where they are talking about pragmatic innovations, okay? Not many, okay? So what happens is innovation, then I also looked at what is innovation. All of us talk about innovation, but there is no single person giving one definition. What is an innovation? What is discovery? What is creativity? These all terms, are very complex, and many people have given thousands of definitions about every little thing which goes on there. But what this particular field offers is that you are trying to do innovations in a space which have some connection over a reasonable time scale, okay, where you are trying to address some practical problems. So it is not something which is, somewhat distant. So there are, of course, even innovation per se, people say it has some connection with an ideation, some idea which has some practical relevance, and even some monetary connections and so on, because many times this word is talked about a lot. If you go to Wikipedia and see the definitions of innovation, it always connects to something related to industry and so on. So pragmatism is a part of it to some extent, but I wanted to put it emphatically because the field as such demands and invites something where its connection with application is established, okay? And it is important for me to also emphasize that applied science is an important thing which is which sort of affects our lives in various ways. For example, I originally by training I am a physics person, but slowly drifted into condensed matter physics and then material science and so on. And material science is the one which goes closer to applications and applied science, okay? And initially what happens is applied science is not looked upon as a high science, okay, but it is a very relevant science to some extent, and many people don't have an idea how important this aspect of material science is. And this is a field of energy and environment that I will talk about, which is completely into material science and what are the advances and discoveries material science can make. See, many of us, if you can, each one of us carries the phone, mobile phone, and inside, if one opens that and you look at a chip, go under a microscope, go under an electron microscope, go everything, there is a whole world of it. The technologies that have been established by, initially by IBM and number of other labs in the US and later followed in all countries, you are having things, the technologies are more like the entire Pune city or a Maharashtra, which is actually being carved on the fingertip. That is the kind of technological advance, and that is all connected. There are roads, there are transports only for electrons, not for cars. You know, you have the entire thing which is sort of millions and millions of pathways. Then you have photonic circuits and all that, plasmonics, whatever. So material science is something which can bring the dreams into reality, and whatever we think, even the big antennas that we do for GMRT, the coating is a very, very special coating, okay, you have to do. And we have been discussing with the GMRT people some 10, 12 years back, you know, Tarun was here and things like that, how to make that coating of highest quality. Without that, those signals, images will not be of that quality. I want to be a sort of proponent of the importance of material science to some extent, and this is very accentuated in the field of energy, which is what I'm going to talk about today. So with a salute to our, Professor Narlikar, I'm sure if he was well, he would have come here, because I have known him personally also for many, many years. With a salute to him for establishing this institute, let's go further. So we talk about the word sustainability. You know, again, every word is talked about, but if you see the United Nations definition, you know, you will see that they say meeting the needs of the present without compromising the ability of future generations to meet their own needs. It's a very, very interesting definition, okay? So it is, of course, some people are there, you say, why do I worry about sustainability? Once my life is over, I forget it. Nobody bothers, right? Sustainability is something which we are talking about next generation and next to next generation, next to next generation. There are some people in some countries, you know, who are supposed to be under some category. They say, I don't worry about what is going to happen after 200 years. Let me look at this now. But many of us do. Especially we are thinking about children, what is their future, and what legacy we are going to leave for them to live very happily, and so on and so forth. So that is sustainability. And if you look at all these aspects which are like sustainable development goals, you know, every little thing, right from education, well-being to life, how are we going to handle all that? These are types of goals. And let us ask each one of us, you know, what are we thinking about? Are we giving any aspect, you know, in our whole daily life or our life in general, what particular thing are we thinking about? And it turns out that we need to do more in this particular area to really do something about it. Now, if you look at what creates a problem to sustainability, all of us know. In fact, as I said, you know, I'm just putting some problems which all of you know. I'm just making a statement of it in my own way and my own perception. Okay, not that I'm giving some new information here. But if you look at these, the numbers are startling. When we are putting CO2, 40 billion tons of CO2 is equivalent we are adding in atmosphere every year. And what we are talking about now is net zero emission. So what are we going to do? You see here, net zero is what we need to achieve to save the planet from a catastrophe. Okay, if you want to do that, we are already putting 40 billion. How to fix this problem? This is a huge problem. And you can see, on the other hand, people who are extremely responsible, and this is, you see here, 400 private jets went to Egypt in Sharm el-Sheikh conference recently, and each private jet emits 2 tons of CO2 per hour and has more than 15 times carbon emissions per passenger in commercial jets. So all of these people went there with so much of carbon being emitted, talking about how to control this situation. Okay, so this is a kind of thing that we have. And you see here, CO2 emissions since this, you see what happens with China, Europe and USA. There was industrial revolution earlier. The periods were very different. Okay, while these, these are the populations currently, okay, and these are the populations 2020, and still we are much smaller, but we, India, China are developing rapidly, as all of you know. So if we really do not do it very responsibly, we can really create a big problem, not for ourselves only, but for the whole world. Because environment is something which is connecting everything. In addition to the policies, the international relations, all those things connect, even supply chains of everything that we do, all those things connect the world. But environment connects it more directly and in very worse ways. Okay, so all the countries have a responsibility to do it together. I must say that many countries in many developing countries have generally kept advising us as to what we should do. Okay, but the problem is they have done some particular things earlier, which is extremely harmful to the whole world, and better all of us do it together. You know, it is not that they have to simply advise us. In fact, as you will see later, India is doing already better in terms of promising something and trying to do about it. I will just show you some aspects. And because of that, of course, the global emissions are going up, the temperature is rising, the ice is melting all over the place, and you know, there are various causes and effects of climate change, as you can see here. These are the causes, but the effects are very hazardous, and I can just, instead of dwelling on this slide is self-explanatory. But if you go further, these are the natural disasters, and many people who are environmentally conscious and connected are actually trying to say that the environmental problems are the ones who are creating this. I can promise you that I am a born and brought up person in Pune, and Diwali used to be very different some 30 years back. It started becoming somewhat different some 15 years back, and even this time when I saw the cold in the morning and the whole atmosphere is entirely different, you know. So even you can feel the amount of rain that we get, sometimes very high, sometimes nothing, you know, sometimes all those things. So environment has become quite temperamental, and it is suggested, you know, of course, there are many people who will like to ask for proof, but the proof many times is in these complex situations and problems is not easy to come, and I will talk about that a little later. So if you do that, and if you see environmental pollution, one of the serious problems is health effect of pollution. You know, many of my students always say that in our generation we are losing hair faster than some of us in our generation. Okay, they say that it is because of UV radiation, you know, and also they are not eating that properly as we did in our particular region. Quality of food is also very important, and what we are getting and things like that. So all these things are affecting us in various ways, and you see there are so many things which even we don't feel concerned over time, and all of us have to wake up to see if we can do something about it. Now, if you see, other problems are there. One problem is water. You can see one problem is drinking water, and there is a lot of population to support too. Drinking water is available only to a small fraction of people in India. Okay, so we are working on some problem on solar desalination. In my Kolkata laboratory, we are starting to work something on solar desalination. Why? Because India has so much of, you know, coastal line. Okay, and if you can desalinate, many people will get good water, and you have solar energy which comes free. It doesn't send you an electricity bill. Okay, and therefore, if you can do solar desalination effectively, you will get a lot of drinking water to people. This problem is very serious, a number of people. Secondly, water pollution and water, you know, purification is another problem that we are working on in one way. Why? Because there are many areas where you find that the water is polluted by arsenic, it is polluted by chromium-6, it is polluted by something which causes humongous diseases to people, and there are poor people who do not even understand what they are drinking and creating a problem for themselves. So there are huge problems, and some of us who are material scientists or claim to be good material scientists, you know, have some social responsibility to at least address one or two of such problems which are of humongous nature and need immediate attention in one way or the other. Okay, then if you look at countries, what different countries are doing, you see here which countries act to protect the climate. You know, I was looking at some data, you know, trying to see, and it turns out that India is one here in the countries who are considered to be taking positive, proactive steps, you know, in the last few years with our announcements of what we need to do, what we want to do, and so on. You know, we see here, Okay, so these are, India is one of them, and I feel good about it. Africa actually is leading the way in some ways. I don't have a time to dwell in details about that, but also the Ukraine crisis is expected to speed up the shift towards renewable. You see, this was the prediction of how much renewable one would go, the world will like to go with clean energy, renewable energy. And within 1 year, the thing has changed. That from 193, this another, let's say 10-15% up, it went, that renewables are coming more, because these kinds of international crises with oil flow getting affected, international relation affecting that very significantly worse, people are moving towards this. And you see here what kind of net zero carbon India has pledged. When I said India is doing well, in Glasgow summit, net zero carbon by 2070, India has promised. That means we have pledged to go there, okay? But remember, 50% of total energy requirement should come from renewables by 2030 to be able to reach to the net zero target in 2017. Right now, we may be just about 6-7%. You know, we have to go to 50%, and that will tell you how many renewable engagements we need to have over time. Secondly, reducing 1 billion tons by 2030 out of the projected this by 2030. You see, so we have to reduce 1 billion tons of CO2 that we are putting. Targets are so huge. When I read this, in fact, Dr. Shivaram, who was the former director of NCL, had prepared the statistics based on this slide, and reducing the carbon intensity and produce 500 gigawatts of renewable energy by 2030. Okay, so we are having targets which are absolutely huge, and if you are a pessimist, there is no hope that we will reach there. But if you are an optimist, you will always say that at least some particular level we'll reach, and unless we set some difficult challenges and difficult goals, we will do nothing. Okay, so better say, look there, this is where we want to do. Okay, so the same when John F. Kennedy said we'll put the man on the moon, there were 90% of the people who were skeptics. Okay, but somebody has to make that target, and then you move. Even if you reach half, that becomes a success. But these are the huge targets that we have put. Then if you have to see how to control this problem, you know, how to control this problem, then you see how much the greenhouse gases are emitted by the things that we do, and making things, electricity, coal, growing things, agriculture, and you see here getting around, it is 9%. We all talk about pollution, you know, we all talk about transportation and moving to electric mobility. Okay, everybody is saying let's go buy an electric car because it is good. Okay, it is sort of reducing pollution and so on. But transportation is only about 9% creating pollution. But there are other things which are not receiving the same attention. When I looked at this in our discussion with Dr. Shivaram, you know, these particular things here, you see, the problem is that this is only 9% problem that everybody is concerned about. Okay, because each one of us has a vehicle, and we want to say, okay, this is creating a problem, let me have my next vehicle, which is an electric vehicle, so I will contribute in my own way. This is like Lord Sri Ram, the Ram Setu, that car, you know, she was doing something, adding to that, so everybody's thinking, okay, my next car I will buy this one and so on. That is not bad, good beginning, but then that is not the only problem that is going to solve this in a big way. Okay, when I looked at this particular thing, our states, okay, this is a paper from IISc, and when I looked at all these states, look at the population, look at Maharashtra, you know, and then per capita income, like this, and number of registered motor vehicles. See here, Maharashtra vehicles, and number of other states, UP, you see here Uttar Pradesh and things like that. When you sit with this kind of a slide, you know, it is very interesting to see where the problems could be, and it is an integrated solution that we want to find out. Environment and energy and flows of economy, you know, they connect everybody. You know, so it is not simply that Maharashtra acting or Uttar Pradesh acting will solve this problem. They have to collectively have certain solutions which will uniformly across the board handle these kinds of problems, then you can go. So this slide is very revealing, and how, where the incomes, so you see here, for example, in Maharashtra, the per capita income would be 62,000. Well, there are states where it is only 13,000. There is a disparity. You need to be equitable, you know, in terms of progress. You need to be somewhere where you are trying to balance everything across, and then make the flows of all entities, flow, supply, flow, education, everything, which will address this disparity and non-equity of opportunities, resources, funding, and things of that nature. I'm sure the politics people address this particular problem. And then India has another problem. We are here in Pune or Bangalore or Delhi, we are grid connected, and we have a lot of power at our disposal. Okay, we do a lot in terms of grid power. We just switch on something and we have a power. It comes from some central area. But there are 70% people who are deprived of power. Okay, and in fact, some of them like this, you know, he has a mobile phone, but he needs to move towards a taluka place to charge it. Okay, and as I always say, he doesn't send SMS to every competition like Kaun Banega Crorepati to lose his charge. Okay, but he needs a charge every week, so he goes, sells a vegetable somewhere and gets charged their mobile for a week. It works for him. So can we provide? So we have produced in our lab, you know, we made solar cells and we have made a solar cap. Okay, so the farmer working in in his farm will have his mobile charged within, let's say, 1 hour. May not be in 15 minutes, but in 1 hour as he works in sun and so on. So small solutions can be provided to such problems. Okay, so there, all this particular scenario tells you that we need to make a transition from a polluting scenario to a one like wind energy or solar energy and clean energy. And you can also see that you have different options there, and the state of global renewable energy employment. There are many young people, so I wanted to see if they are working in some peripheral areas which relates to energy, there will be tremendous employment coming up. Even employment shift. So many jobs are going in coal, oil, gas going down, and in renewables of all forms, the employment is going up. This is a statistics, and even in the world and in India also, you will see that this particular path will rise, because in 2030 and 2050 and 2070, we are saying 2070 we are saying we are going to make a progress. So India is committed to that. So there will be more job opportunities here. Okay. Also, in managing our energy, we have all sorts of energy sources like this. Okay, so what one tries to do is, when you have energy consumption, this was an old one, 2007, but more or less the same. Transportation is more oil, industry more oil, as well as some of this natural gas, and then electric power is more coal and so on. So what we need to do is, we need to manage the energy mix in such a way that we use renewable energies and keep changing from non-renewable to renewable in a very responsible way and in a very strategic way. We cannot just say some energy forms, renewable energy forms, can do something good in certain sectors, but they may not be able to be applicable to some other sectors and so on. Also, it is very important to realize that there is this graph where you are talking about human development index versus per capita primary power consumption. Now, per capita is per person. Okay, it is more like per person. Sorry, what happened? It sort of went. I think I am pushing something. Yeah. So this is like per capita, and you see India is right here. So we have per capita primary power consumption is so low. But when we go here, we'll climb this ladder and our quality of life index will go up by 40%. Okay, something in that range. But then there are many of these countries, their quality of life is the same for all of them. But you see here, Norway, UAE, and Qatar and all, they are spending 10 times more power than they need to have the same quality of life. The graph saturates like this. Okay, so what India needs to do is, India needs to double its input in power per capita, per person, and if you double from, let's say, 1 to 2, we will already climb here, and then we will be already better off in terms of the human quality index. So we have to manage all these particular things in a very interesting way. And then if you want to manage, you can see how much power we can generate per square meter. And why we are so attracted to fossil fuels? Because per square meter, meaning you have some amount of fossil fuel, you generate watts per square meter is humongous. Nuclear generates 500 to 1,000, and it is one of the important sources of energy which we cannot just say no to. Okay, but the proliferation of this requires certain particular requirements, safety and a number of other conditions, and there are geopolitical issues which need to be addressed in nuclear energy and so on. So it is not easily something that, like France, for example, uses a lot of nuclear energy, okay, and they are in fact not making that much fast transition to solar, but Germany is doing that, but then France is borrowing power from Germany. So all these complicated things are happening, I see. So we have to think what we are going to do to this power, and solar is very low per square meter. So this is something like solar is available free, plenty, however it is very dilutely distributed. Okay, so what happens is solar is dilutely distributed, so it is like I need 1 glass of water, but let's say this water is spread across the whole Pune city. You know, how do I get that water? Okay, collection is a problem, focusing is a problem, and so on. So you have to think how to grab this, dilutely dispersed power and so on. So these problems are not easy. Then we are changing the world rapidly. We are moving to electric mobility. We are talking about flying cars. There are demonstrations. We are also talking about driverless car. In fact, my son is one of the sort of senior engineers in Google who is engaged in the autonomous car project, and he has been right from the beginning, and I have sat in this car in California, and moved on the road in California, and since he was a part of the designer, I was safe, I felt safe to sit there. And then what happened was, it is very interesting, and that's where so we went on the road, and then on one road, the car stopped, because there was an engine. Like in Pune, this is a very familiar thing. There was one building construction engine doing something, but the car stopped. The driver was there, but he was not touching the wheel. Okay, the car completely stopped. And then he said, what to do? Then the driver turned around, moved like this, and again took his hand out when he moved across, like that. So he explained that this is what we learn right from our childhood, and this is this machine learning issue. Okay, so machine learning, so what happens is, if he does 100 times that, it will be learned to do that looking at the situation, safely go across and do something, and then that is okay, and so on. So this is what, otherwise the car was sort of programmed to follow the rules in one way, and when the lines, etc., it saw that there is nothing available, it just stopped. Okay, it didn't look here and go there and so on and so forth. So that learning exercise. So there are all these integrated science. So only one problem is not solved by one particular expertise. You need other things to go to. And we are talking about electric vehicles now, but they have been long back. The first full-scale electric vehicle was in 1887. And you see these people sitting on lead-acid batteries. Right now we are talking about exploding scooters and exploding cars and so on. They were really sitting on bombs then. It was discovered only in 1859, and in 20 years they already knew that we need to go electric. Okay, it is only recently that we have this fancy Tesla car and all the entire battery stuff below. We have problems about cooling batteries, what we are going to do, and things of that nature. But I wonder, after 1887, till about 100 years, we did almost nothing until we were forced with this environmental problem, to talk about electric mobility. And it is only in 2015 or so we have started becoming serious about it. So this is a kind of a situation one is talking about. Then we are having next generation device systems like this, which are extremely lightweight devices, flexible, thin, lightweight, self-powered, and many of us wear these watches, etc. But much more advance is expected in the next 10 years. But you need flexible batteries for them. You need some power sources for them. Okay, so all these particular devices and advances which are happening are going to be very, very important, and the whole set of new technologies are coming here, even all that. Then we have robotics, AI, machine learning, and so on. We have other fields coming. IoT, this is a slide which is made by Dr. Smita Chaturvedi here. She likes to think about IoT and smart world coming, smart hospitals, smart this. You see here, sorry. Everything is smart. Smart city, smart hospital, smart highway, smart factory, smart city. It appears to me that only we are the less smart in all this business. Okay, everything is becoming too smart for us to handle. And in all this particular business, we never realize how much power is going to be required. Okay, we already, when we have our fingertips on our computer keyboard, we feel that it is free. We never feel that there is some power getting consumed. Okay, so when there are going to be complete of IoT and all this, to the level of smart everywhere, where is the power coming from? And it is calculated that even these data science centers, okay, they are humongous power consuming centers, and people are thinking how renewables can be used there. So you are not going to pump in liquid oil and fuel and diesel to power all these data science centers and everything, because the pollution will go up. So how renewables are connected with all our dreams and some actions is important. Now let me come to some of the things that people do, people like us are engaged in. So we do energy conversion, energy storage, and energy conservation. Now you can have solar cells, you can have solar water splitting for hydrogen generation, you can do solar energy use for different things. And there are, as I said, material science, there are many number of materials that we work with. Okay? Now storage is like batteries. Now we have lithium battery, sodium battery, aluminum battery, and so on. A number of other things are being done. There's a lot of research. This slightly older slide, but you have so many materials we play with and try to do something. Okay? This is LEDs and stuff. Let me go in solar energy. The advances is traditionally you all know about silicon solar cells. We are all aware about silicon solar cells for the last whatever number of years we have been there. In fact, I will tell you that early 80s, there was a project on solar energy, even in National Chemical Laboratory, on polycrystalline solar cells. Professor A.P.B. Sinha, who was the head of the physical chemistry division, started that project. Then in the next couple of years, when I was just a young PhD and so on, Professor V.G. Bide, there was Professor K.L. Chopra and Professor Barua from Kolkata, they started another project, amorphous silicon. Okay, and we worked on it. I had gone to Japan to get training and work on amorphous silicon. But suddenly, in late 80s, I don't know what happened, the entire solar cell research went off. And now we wake up in the last 5-7 years to say that solar energy is required. Everybody started with what happened to solar cell research. Okay, so this is where sometimes, not that the scientists were not aware of this, okay? And some policymakers were also aware of this. But in India, somehow, we don't have a sense of continuity. That is my personal observation. Even when you sit in DST, PSC committees, program advisory committees and so on, you go make a presentation, you win a project. You say, okay, I have got a grant of 1 crore because I presented something. They say, excellent. At that time, the scrutiny is very good. Okay, they say, okay, this question, that question, they keep asking. And then they say, grant the project. Okay, if your project is good, you are granted. After 3 years, if your project gets an excellent grant, you are allowed to do one more. Okay, but it is not insisting, you don't insist that you do continue with the progress that you have made. Okay, then you write another project. I have one project, one on solar cell, then the next one will be battery. Okay, so then I forget about solar cell. Then no industry has even, and that report has not gone to any industry that this guy has done something good, can you take it up? There is nothing which connects people and keeps an eye on the progress. There is no agency to be able to do that. So what we lose is scientists do their job, and after that, they have the fancy of doing something else, and that freedom has to be with everybody. But then whatever they have generated, is it going anywhere at all? There is no scrutiny of that. So we are all kind of going into circles, and there is no progress where the continuity and the rising graph is there. So we are like scattered, doing different things, each one leading to few good publications and this, that, and the other. But then, where is it going? And we have to be very concerned about that. So these new solar cells which are coming are entirely different generation, and they started in 1992. This solar cell, which is called as dye-sensitized solar cell, was developed by Professor Gratzel, okay, in Switzerland, and he actually used the principle of the photosynthesis in plant leaves. Okay, and he said these leaves has chlorophyll, and that chlorophyll is absorbing sunlight in the visible region and then doing the redox reactions and taking the growth and all those things. So using that, he developed a concept of solar cell which is called dye-sensitized solar cells. And we have, so many of us have since then worked on it, and the principle is so interesting. You see, the way nature thinks is different than the way we think. Okay, why? Because this leaf, which is a solar cell produced by nature, okay, is something which is expendable and cheap. The leaf does its part, and then after a month or 2 or 3 or 4, the leaves fall down, okay, and new leaves come. Okay, while we are making a solar cell, we say, I want high efficiency. By the way, this efficiency of the natural process is more like 1 to 2%. While we are saying, I want 40% solar cell, and I want that solar cell to live for 30 years, okay, unless it goes into some accident and falls down, okay? Why we are doing this? So now he thought it differently, and can we make solar cells which may be just 7% efficient, okay, but so cheap that I can just buy and maybe in a few months just throw and buy something else. So those kinds of things are coming up. Secondly, you can see if these kinds of solar cells exist, you know, can we have the entire building coated from outside with a solar cell? Like non-technical people come, paste one layer, then they come and they paste another layer, connect, make a solar cell, go there. Can we do something like this where the building can be a light harvester and so on? Many new concepts are coming. Then there is something called this new advance that many people know is hybrid perovskite. This is some material system which has come up, which is called hybrid perovskite solar cells, and this is like this. Okay, I like this picture, which is where things are moving, so I thought I will share with you. You know, what this thing is where you have an organic, inorganic hybrid material. Okay, normally we are always thinking about organics and inorganics, but then there is a boundary layer between them where organic chemistry and inorganic chemistry are coming together, you know, to make some wonders and new materials, new solar cell concepts and so on. And that's why now many people, earlier, you know, many people say, I'm an organic chemist, I don't know what you are doing, you are inorganic. You know, these kinds of branches were there. Now there is an integrated view. Okay, so multidisciplinarity and interdisciplinary sciences are the key, okay? Because where the problem is important and not what I can do and what he can do, okay? What we can do is something which is important for the problem to get solution to that particular problem, and that is where your own expertise is one of the things that goes there, and you will not get a problem which is what you will only solve because it is in your field of expertise. You need to peep out of the window and try to do something else there. Okay, so what happened? It's probably the battery has run out, or Samir, are you there? Ah, the arrow. Okay, so this is something which is the hydrogen as fuel, and all of you know about it, but you see current price of hydrogen ranges between 8 to 10 kg per kg, while DOE has set the target to 2 to 4 kg by 2020. This was a target by US DOE, and it has not been completely reached, but that is where the people are, and hydrogen economy is something which is important. Okay, you can change the battery, all right. Then people always talk about hydrogen colors. This is a definition, okay? Because hydrogen can be produced by different methods and the sources. For example, if you produce hydrogen from natural gas, or you produce from renewables, you produce from different sources. So people said, oh, I'm working on pink hydrogen. It is as if, you know, you are working on astrophysics, I'm working on physics, they say I'm working on pink hydrogen, or I'm working on green hydrogen, and so on. What does it mean? Green hydrogen is something, okay, is it working now? Okay. So this is, green hydrogen is the main one, which is basic electrolysis that all of us have done in our labs in chemistry, if we had chemistry at all, okay? And that is something which is very important, totally based on renewables, okay? So use renewable energy to do electrolysis of water and get hydrogen and oxygen, and use that hydrogen in a fuel cell, okay, to produce energy and so on back. And when we do it with sunlight and sun energy, then you are actually completely getting it free, no bill again, okay? But again, the dilute spread of solar energy is a problem, how efficiently you can do it, how much in quantity you can do it, what efficiency of conversion is required, and all those things, and categorize, okay? And this is that basic green hydrogen, take something and then go here, produce this, and then store the hydrogen. It is not easy. Storing hydrogen is a big, huge problem. Okay? Now you imagine a situation. Right now, many people who are buying electric vehicles, they are thinking about safety. Many of our friends are also thinking, I have a big bomb sitting there. You know, if it explodes below your seat, you know, what are you going to do? Okay? So the safety criteria are there. Now, people are saying that in another 10 years, fuel cells will be running the cars, not batteries. Okay? So you will have a cylinder of hydrogen. How safe you will be sitting on cylinder of hydrogen, which if it explodes or leaks out, hydrogen and oxygen can produce a big bomb. Okay, even in our lab, you know, when we use hydrogen gas, it is diluted to about 4% in argon and things like that. Now, if you want to have hydrogen, you know, as a cylinder carried, then what are you going to do with this fuel cell and things like that? So safety issues are so humongously complicated that we have to think about it. But the human spirit is very, very interesting. In spite of, if someone is saying, oh, in that case, I don't do it. No. We are still doing it. Scientists are still looking at safety, how to get there, and there may be a few accidents here and there, but eventually there is a hope that we will succeed even with hydrogen technology. And that spirit is something which is driving research and driving the technology for everybody to follow. Oh sorry. I think something I push while talking. All right. Okay, so the other thing is CO2 to fuel reduction. Look, CO2 problem I indicated to you. Now what we need to do is this CO2 which comes out from there, you have to convert into either methane or something or carbon monoxide, which is a usable gas for some chemical reactions for fuels or something. So we need materials. See, CO2 molecule is a linear molecule which is robust and it doesn't adsorb easily to be able to convert into something else. Okay, it is a very inert type of a molecule. So what we need to do is provide some catalyst which electronically will interrogate the CO2 molecule, adsorb it, okay? And if light or any other source is done, you try to dilate the CO bond in some way to change it into other molecules. So there is tremendous research going on these, and we have published several papers in this area. And similarly, there is another issue which is nitrogen, ammonia synthesis. You know, you need ammonia, the fertilizers and everything. Ammonia is very important for us. And there is so much of nitrogen. Nitrogen is another inert molecule, N2. Okay, and it is a very solidly inert molecule. How to make it react with hydrogen and then convert it into ammonia, which is usable in different ways and so on. So this is another problem which we are engaged in. And what we are doing in our lab is trying to use science of low-dimensional materials. After graphene, these two-dimensional materials with this Dirac cone type of a structure, band structure, these things have come into play, and where are carbon nanotubes or buckyballs or any other quantum dots, these are the types of materials we use to do something, and we have done several publications on these kinds of areas. And it is important that two-dimensional materials are many, and many of them produce very interesting electronic states, electronic band structures, and all of you know that 3D, 2D, 1D, 0D, the band structures, quantum effects are entirely different, and we are trying to utilize them, you know, to do all this hydrogen, water splitting, CO2 reduction, materials manipulated to be able to do that. Okay, and then there are interfaces everywhere. In all the devices that you do, interface between two solids, interface between solid and liquid like in a battery, interface between a molecule and a solid, interface science is something that my group does and many of us in India are doing. It's a very important condensed matter physics and science that we do, but we do in the interest of energy research. Okay, now we also have to keep an eye on the abundance of elements on Earth. You see here, this 32% is iron. Okay, 30% here is oxygen, and then silicon is 15%, and then this magnesium is here. Okay, while this is the material, we are using rest of the elements, and these are elements of clean energy so far. Try to understand that in our battery that each one of you are carrying in your mobile, you have LiCoO2, lithium cobalt oxide. Now lithium is extremely rare. Cobalt is also extremely rare. Okay, these are expensive elements, and we are using that for the battery. So now the tremendous drive is to use iron, for example, or use silicon, or use magnesium, or use nickel to do our activities and make batteries in this particular area rather than using some very precious elements which are in limited supply. I will come to that in a minute. So there is also a lot of science going on recycling, and many of young students would be aware because they are much more conscious of how you do recycling and things of that nature. Okay, so we cannot use, and I will come to one point there, and this relates to circular economy. Okay, so what are we going to do to actually get back a lot of materials? Many of you know that we have these toys, and in that there are 1 or 2 batteries we buy. That car moves, you have remote control, it moves here and there. My grandchildren play with that. But after that, what we do to those batteries? Generally, most people throw it in the dustbin. Okay, and that is lithium gone there. That is cobalt gone there. Nobody bothers about it. Okay, so there has to be circular economy, which is very important. There has to be a huge drive for battery collection, user battery collection, and do something with it. Okay, and solar energy also, you have to think, and Shivaram has done a lot of work, is not renewable until the panels are recyclable. You know, nobody bothers about this. Okay, and what you need to do is, we think that solar energy, once it is done, I have done my social responsibility. Okay, I have fitted solar panels, and I am having a shower or hot water by solar. Sometimes if the water doesn't come hot enough, then we say, kya ho gaya? You know, we see there are all those things, and we say that is my sort of individual solar responsibility. But no. If those panels, and you see here, there are many points, you will have to study what are the elements there and all that, and how you want to recycle. We cannot call solar energy as our job done just by fitting some solar panels. Okay? Now, here you see the solar panels, numbers are rising, and this is the amount of solar panels which are going to be lost. So see, mass of photovoltaics in service and cumulative waste in this region. See, in India, you will have 7.5 million tons by 2050 of panels which are dumped. What is happening to that silicon? And you know how much effort goes into making silicon from sand. How much carbon footprint goes there? You know, what furnaces are running, how much fuel is going, how much purification technology we are using. Silicon is also used in integrated chip, every mobile phone, you know, every memory in a computer. Silicon is a technology material, and we are using so much, and it is because sand is available in plenty, we use that. But the amount of CO2 we are producing in purification technologies, there is no audit. There is no audit, and there is no care about that whatever we are using comes easy. We just do everything, right? And memory is stored. I want this much computer, this is big computer, all that. And you produce so much of trash here, you know, what are you going to do with that? Unless you recycle, you will have a problem with that, okay? And then lithium and cobalt, you know, it is Chile and Argentina, they have a lot of lithium. China has some, Australia has some, and China has already bought some hills and mines in Chile and Argentina. Okay, India is recently saying that some region in Maharashtra or something, lithium may be there, and so on. We have no lithium. Okay, so there is a lot to be done about lithium, and the question is whether we should run with lithium or we should use some other elements for battery. We'll go further and I will explain to you. Okay, so they are a problem here, and therefore this battery material, after the batteries are crushed, they have to be taken through the whole cycle to separate out the materials again, because when we take out minerals from mines, you know, there is a lot of energy gone there, and it is going from bad fuels, and we have to ask ourselves how we are going to recover the energy, and how that CO2, which is what we are contributing to, is to be mitigated in a very intelligent way, and so that we are not doing this problem, which is, we are not at least adding to problem if we are not solving it, okay? So there are ways to value also, there are a number of things we can do, and you see this particular computers, batteries, everything, this particular waste, there are so many elements to be recovered from there. All the chips, computers that you have, and you will have to do recycling of all this to generate all this, because if we are every time adding that in generating that, this is going to be a problem, because we are just buying a computer, after everything we say that no, khatam ho gaya, you just dump it. And where is it going? You know, what all those precious, what is happening to the gold there? All those lines connecting gold, platinum, this, that, and the other, what is happening to all that? We are never concerned. We have never been concerned, and now is the time that we need to be concerned about, because there is energy going into making that, there is energy going into making to purify them, and there is CO2 being emitted, and all this cycle we have to worry and think about what to do. Now, these are very nice options like Atmanirbhar Bharat and Make in India projects. Okay, so these offer us opportunities, but will have to be created through industry, academia, government, synergistic cooperation. We talk about Make in India, we talk about Atmanirbhar Bharat, they are extremely good thoughts, but there has to be a parallel ecosystem developed and understanding developed to be able to do an implementation of this in real terms, okay? So I have just made this slide. So if you take government, they have national interests, they have international relations to worry about in all this. Then if you take academia, okay, then you have academic interest, career interest, and also national interest. All of us are having national interest, okay? Then if you take industry, they have growth interest, economic interest, okay? And you have national interest. So all three have national interest, right? But their other interests differ here and there. And how to build a synergy between these. What to do with these gear wheels so that they will synergistically operate to solve some problems, solve some huge problems, is something that we need to think about. And here you see academia, industry, mutual confidence and respect, mutual value of interaction. Only confidence and respect doesn't work. If we scientists do something which is valuable to industry, only then when they are coming. And if the scientist has something which he can contribute, then the industry will come, and so on. I will give some examples. Otherwise, what happens is, let me compare music versus noise. Okay, music is something where the orchestra plays, and you know, in a harmonious way. All of us have seen that. We say opera, a nice music, nice song, synergistically everything happening. Now you imagine another situation where all these people, all are experts. All are experts, okay? So, for example, I know both Somak and Smita, you have, I think, sitar, right? You play sitar. So, each one of the people who play, imagine a situation that here is an orchestra sitting, violins, there are 10 people, there is guitar, sitar, this, accordion, everything, they are sitting. And you don't tell them anything, and each one is an expert, super expert. But they start playing on their own without any harmony, it will be simply noise. So what happens is, academicians are doing very good, industry in their own right is doing something, government is doing everything, right? But if there is no music, you know, there is no synergy, it will be simply noise, and we'll continue to add to noise rather than music. So our intention is that it is the same situation like this, that all these gears are supposed to work in unison so that this will move smoothly. Now just take a little distance away the gear, it will produce noise and the whole machine will stop. Okay, so that is why the synergy and noise is very, this comparison I give, because it is not the question of expertise or intent, okay, like national interest. We all are interested, okay, but how to bring it together so that it is harmonious and try to sort of merge into one unison so that it is effective. Okay. Now, we have done some work. I don't want to bore with you details. You can see our website. We have been working on carbons, and as I said, we have done something on things which are like working on waste to value. Okay. For example, these are leaves. We made some. This was a tree in front of my office in NCL, and every time when we were going out for a cup of tea with students, we found that the guy was taking all those leaves and burning them. So I said, keep it. And we just tried to burn them appropriately and produced carbon, which was for a battery grade carbon. Okay, so we then actually when we published this paper, this is one of the highest impact journals at that time. I got a call from a Canadian professor, and he said that this paper is wonderful because Canadian symbol is a leaf. Okay, so he says in fall we have so many gigatons of leaves. Okay, and he got a project from their NSF to convert those leaves into carbon, and that was fun. So we just had some kind of thing. Then also these few things we did was, this is value-added journey for a shredded office paper. And we produced a very high-quality battery-grade carbon using shredded paper. 2-3 things did, and it turned out to be in the New Scientist. They called us waste paper turned into super sponge battery and things like that. And we have established in IISER laboratories like this. Okay, and in fact, I went to IISER in 2015, and in about 3 years' time, we developed these laboratories there. Similar laboratories have been established in NCL. I was there for about 9 years. We started energy activity in NCL, and Dr. Shivaram was a director then, and he supported our activity. We got big funds from MNRE, DST, and so on. Similar laboratories have been established in IISER. These are the laboratories, and we are making batteries. You see, this is a battery which is called 18650. It is a big battery like this, not your AAA or AA, it is bigger than that. And this is a battery which is 26650. This is a fat battery like this, you know, which sometimes you use for a lot of power and so on. These our students, Abhijit Patil and number of other people in our lab, you know, they are working to make these batteries. And we are, see, I always see every other month, we have made a first battery in India. We have not been in sending that kind of news, but we have been silently working, because we can always say that we have made a first battery, but nobody says how quickly it died or what was its capacity or something. So we are a bit, we feel really responsible before we announce to say that, okay, we have made this battery and it is fitted and now it is running for so many cycles and so on. Only then we will go into the news. But we are making batteries in our lab. Then I am now, as Professor Shomak said, that we have this laboratory, Research Institute for Sustainable Energy, where we are working on batteries and supercapacitors, hydrogen energy, CO2 reduction, and clean fuels. And this is just from the website. Last moment, I just put the slide. And we have established, and this is done by Dr. Purnendu Chatterjee, who is a billionaire, but he's a PhD from Berkeley, and he was an IIT Kharagpur alumni. Dr. Purnendu Chatterjee is fondly called PC, Purnendu Chatterjee. And there is this Chatterjee group. You may go anywhere, even in Pune, there is TCG. Okay, there are a lot of activities. They have TCG Life Sciences, TCG Digital, TCG other things, real estate, and all those kinds of things. And he decided to establish some outstanding center in India, research center, to have, so we have verticals like, this is Research Institute for Sustainable Energy. There is another which is the Center for Neuroscience, Advanced Neuroscience. Then there is third one, which is Institute for Advancing Intelligence. Fourth one, and so on. So there are different types of institutes, verticals, and Professor Shobho Bhattacharya, or Sabyasachi Bhattacharya, who was the director of TIFR for in around 1905 to 10. He's the overall director of this TCG CREST, and we are developing laboratories there. And you can see, Shomak, I was telling you, this is our laboratory energy, that we have got enough instrumentation there now already set up. So it is several hundred crores have been spent to develop labs. This is the RICE laboratory where I'm sort of monitoring. So this is a not-for-profit Section 8 company. Okay, this is for education, and a laboratory is established in Kolkata. Many of you, if you happen to be in that region, you are most welcome to visit us to see. And this is all being done to establish in the field of energy. Okay, this is a whole TCG CREST, another section of laboratory for making batteries. And we want our almost 65 to 70% research is going to be in the field of batteries, and we are making batteries there in IISER Kolkata. And we will be interacting with many people, and we are going to make batteries which are also specialized for space science, specialized for example, if you say space exploration, you know, those batteries are different. You have something going on Mars, okay, and the power, solar power is to be stored. Then there is cosmic radiation. You have to have radiation hard batteries. What is going to happen there? Because the battery should not die there in that path million miles away and so on. So similarly, you have DAE robotics. You know, those batteries are different. You cannot go to nuclear radiation, things of that nature. You have defense batteries which go with missiles, okay, and so on. So we are going to specialize on a number of things, and this center will sort of flourish in time to come. And we have worked, I was talking about industry, we are working, my lab at IISER has been working with KPIT company in Pune to make batteries, and we have worked on sodium-ion battery. As I mentioned to you, lithium is a huge problem. We are in short supply. Unless we are smart and recycle, we have a problem. So IISER and KPIT sort of decided to do. You can imagine Mr. Ravi Pandit, who is actually a visionary. Okay, he is the one who is very interested in clean energy. On his own, through a common friend, he approached me, having heard a little bit about our clean energy operation, and he said, let's do something. And we took about 4 to 6 months of discussion what to do in batteries, whether to do lithium, whether to do sodium, because they have also business interests. Okay, and after that, a project started. And you will not believe, some of my students here know, every Saturday for 2 hours, he came to IISER. Okay, almost 150 times here, weekly meetings. He and his 3-4 people came, sat, and we kept on developing, and now we have a battery, sodium-ion battery here. Like this, they have manufactured, and 6 of my people are there. So let me just show you. The reason is lithium to sodium availability ratio is like this. Okay? In Earth's atmosphere, inside Earth, lithium is that much, while sodium is that much availability. Similarly, cobalt is that much, and Fe is that much. Why not do with Fe? Okay, right now, in our pockets, whatever mobile you have, the battery is based on lithium cobalt oxide. So both small elements availability, okay, expensive. Okay, they are not available that much in quantity, so we need to work on elements using iron, using magnesium, a number of other things. So we are doing a lot of work. That's why the KPIT decided that instead of lithium, let's work on sodium battery. And you will see that we have done something, charging, fast charging. 4C meaning 10 minutes, actually it should be 6C. In 10 minutes or 6C means it charges fully in this particular time. Okay, so we have all these particular things. We have made this battery, and then I don't want to go into details. We are making 14 ampere hours, 1000 cycle batteries and so on. Now this is the picture of the team, and Sarika, Anil, Yogesh, Mandakini, and Ankur, they are all students from my lab. Now they have a job in KPIT, and they are running the show. Battery show there. So you see, this is where we had this interaction, and they are now the chief architects of the battery program at KPIT. Similarly, we have another one on lithium-ion battery with a company LiveGuard. Okay, and in LiveGuard they are mainly interested in 2-wheelers, 3-wheelers, and they are already in this inverters market and so on. So they said that for us, sodium will be heavier and other things. So for 3-wheelers, we want to do lithium. So we have done in our lab batteries like this. Okay, they are pouch cells. Okay, and they are made, and we have made batteries. Now recently, 25 ampere hour batteries with 1000, actually more than that, 3000 now. Although it comes down to 80% of capacity, all that has been done. So done these batteries with a company, LiveGuard, and now KPIT is also working with Agarkar Research Institute to do microbial fuel cells. So microbes do many things which are very interesting, and I think biology people are getting connected with the hydrogen technology now and trying to see, because actually many of you may know that microbes, actually there is copper mining. There are microbes who sort of do redox reactions on sulfides, and copper extraction from mines is done by microbes. So microbes can do many funny things, and now people are trying to genetically engineer them to do something which may be, let's say, taking out lithium or taking out sodium from trash, battery trash, and things like that. Okay, so these are microbial fuel cells, and a lot of action here. Finally, let me just show a few slides, just jump quickly. I know I'm kind of running over time. Yeah, 5 minutes, more than that, and it's all done. Okay. So in terms of innovation, as I said, there are many definitions, but let me show you something that comes to my mind when innovation, how people think differently. Now, all of us know these kind of lighting systems. Okay, and these are lighting systems, while nature has lighting systems which are different. Okay. We have here tungsten, you have plasma, you have semiconductors. Nature is not having any of that. Still it lights beautifully. So now people are thinking, how can I light something which is based on some of these understanding this nature and try to do that. This is biomimicry. So I'm saying that innovation is something where something like this can be done. Let me show you, let's go further. We all talk about memory. This is what our memory is, while our brain does not have either a semiconductor or a ferrite or anything, right? So this is called, long back I had heard a talk about this, configurationally accessible memory. Our memory is interesting, okay? It doesn't work digitally. Like many of you would say that if I come again tomorrow and I am heard somewhere and I put a tape here, you will still feel that I am the same person. You agree with that. But in computer, if it is 110 is flipped, you say it is not the same number. It is not A, it is something else. Okay, so it is configurationally accessible memory. Very interesting structures are developed. Finally, let me not go into all these details, but let me give you one example and stop. This is where this beetle is called Namib desert beetle. Many of you may have heard about it, but this beetle happens to be in the South African desert completely, and the desert is completely hot. There is no water, but has sea on all the sides, so there is a lot of vapor comes out. So what this beetle, for his survival, what he has done is he has developed a method of trying to get water from air directly, from humidity, which has come from the humidity in the air. So what he does is his back here is established of hydrophobic and hydrophilic components. So he has all these crevices and something which are developed in such a way that there is water hating and water loving portions there. So what happens when the vapor condenses on his back, okay, the water hating things go and it goes towards the water loving part and it produces a drop. Then this particular beetle makes a back like this and that drop comes and he drinks the water. Okay, so this is a very, very interesting thing, and I have a movie which I think I can show here. I can just click on this and then we stop here. Let's see if it works. Yeah.
By 2025, nearly a quarter of us could be living in places where water is scarce. Now, scientists trying to tackle the problem have turned to a tiny beetle for help. The fogsand beetle is native to Africa's Namib Desert, one of the most arid areas of the world. But what it lacks in rainfall, it makes up for in coastal fog. And it's this the beetle depends on for survival. It basks in the fog, standing upside down on top of sand dunes. Its back is covered in bumps that have water-loving tips and water-repelling slopes. This structure encourages tiny droplets of fog to stick to the surface. As the droplets coalesce to form larger drops, gravity causes them to roll down its back and into its mouth. Now, there are several fog collecting projects across the world, but improvements are always welcome. Scientists in the UK are replicating the pattern to design roof tiles that trap fog water. The tiles could help hospitals in parts of Africa collect sterile water to make medicines. Everybody needs water to live, and this clever beetle will continue to teach us innovative ways to make the most of it.
Okay, so just a couple of slides more. Let's get back. Yeah. Okay. All right, so they have made this like a beetle back. Okay, and this was the earlier work by Arizona State University, but number of people around the world are now doing this. So beetle has shown the way, and where we were earlier talking about artificial rain and all that, right? Putting some kind of the nucleating fluids in the through helicopters and so on. But now people are doing this. If there is fog, you can collect water, and this is potable water, drinking water, fresh from air. Okay, all right. And so I say that all these are some figures from our publications. Okay. So nowadays, in certain age group that I am in, we think, is there any of these equations, even directly or indirectly, can help somebody like that who has serious problems? And I think we should all think about it. And I would just say that this is what Dr. Shivaram has connected. Human intervention, applying cautionary principles to sustainability thinking. We are already talking about sustainability, but we have to think whether this our intervention is going to solve this complex problem or add to it. Okay, so this is what I've been discussing with him, and there are unintended consequences. So this is like a push-pull oscillator and amplifier, and something keeps happening, and it can go wrong in the other direction and become chaotic. So we have to be a little cautionary about this. And finally, this is the slide which I show. This is IISER, and this is Ravi Pandit, the KPIT founder and CEO. And this is the community. This is a 2018 photo. I'm very happy that in 2015, when I went there, we started Center for Energy Science. We didn't have any activity. And in 2018, in-house conference, we have so many people interested in energy in IISER, and I felt proud when I saw that in 3 years this happened. And this is what I leave you with. Thank you very much. Yeah. Sorry, Shomak, for a little bit. Okay. Yes, please.
Thank you so much for this amazing
Thank you. Thank you.
various aspects
Yes.
of sustainability and energy research.
Thank you.
You've touched on some things that you've done yourself.
Yes.
At the end.
Yes.
I'm sure a lot of people would want to know more about
Sure. Yes.
those issues as well.
Yeah.
We have time for a few questions, and there are people out here with portable
Yes, sir,
microphones. Please put your hand up, and I'll get there. Mayuri Shamtandon, please.
Wondering, you were talking of extraction of materials and recycling. Can one put some theoretical limits? What is minimum energy required for extraction and recycling? Are there, do these things exist?
Yeah, so recycling issue is just beginning to unfold in the last few years, okay? And what happens in the process of recycling also, there will be some energy spent.
Yes.
And people are trying to insist that that has to be renewable in some form. But the equations have not clear yet, because this field has not matured to the extent where this calculation has come up.
Yeah, what I mean, can there be theoretical calculations?
Technically, yes, but even, since I personally don't work that much on recycling, I have no clear idea about how much it would cost, I think, yeah. This is a problem which I'm concerned about, and, some people I know are working, but I don't have numbers to give you. Yeah. Yes, sir.
Yeah, basically, I want to highlight on the...
Can you be a little louder?
Yeah, basically I want to highlight one from the slides itself. Like you said that...
No, I can't hear that clearly, sorry. Is it on? Go ahead, hold it closer a little bit, yeah.
Yeah, basically I want to highlight one problem. Like you said, sunlight is dilute in nature, and we cannot get the hold of whole sunlight, which is spread across the spectrum, like in the city, like this one glass of water is spread across Pune city.
Yes.
So I'm thinking, like, can we use any concave lens to gather this sunlight which is there at one point and burn the water inside some container? So
in fact, all these
hydropower,
in fact, people have thought, of space lenses also. Antenna, space lenses, number of things. But you have to always think of the whole economics of what you do, and how to collect that and things of that nature. It is not easy. In terms of, suppose you have a space lens somewhere far away and try to do things and so on. It has many, many issues. You cannot focus that. But however, there are sort of farms of several 1,000 acres in some places where you have different lenses and mirrors, focusing on reasonable spot. Okay, in Spain and number of other places it exists. These are called concentrated solar power, CSP. Okay, but there are the types of things you are saying are there in smaller regions. not for the whole earth to the extent it is possible. While the requirements are everywhere, so it is not easy to apply this everywhere. This is called CSP, concentrated solar power, and it does exist at places like this. Yeah.
Yeah, another question is like, can we engineer or genetically engineer some microorganisms which live on carbon dioxide? Like we have, you have shown a video where a beetle is converting fog into water.
Yes.
I'm saying of some beetle or microorganisms who live on carbon dioxide.
Yeah, in fact, it does happen because you have CO2 and H2 going into a microbial fuel cell. The reactions happen, and those things are already there. If you just see, say, even on the internet, microbial fuel cells, there are many microbes which are engineered. Now people are entering into this field. This is not mature field so far. In fact, at Rice, we have now appointed an assistant professor who has an expertise in microbial fuel cell area. Okay, and she is going to work with our, bioscience wing to actually develop some techniques to do that. But they are not expert in genetic engineering. There are some other people who are doing that. Okay, so it is something that is a very doable problem, and CO2 fixation, nitrogen fixation, I showed you, even the cells do it, biological microorganisms. So research is going on, and as I said that I'm pointing out some problems which are all connected. Okay, but I'm not expert in all of that because I'm not a microbiologist. But I know that this is being done. Okay, so.
Mayuri, do you have,
yes,
back,
sir.
yes.
Thank you for an excellent talk,
Yeah,
Professor.
thank you.
I would like to ask two questions. One is pertaining to the battery technology. I know that most of us shoot for very compact, high energy density batteries, but that typically implies that they're going into some kind of a mobile unit which you need to carry it with you. But there are also applications where we do not require that, especially where power systems for regions are concerned. We require a storage facility which need not be mobile. And it could be low energy density, it could be large volume.
Yes.
Could you comment on whether there is any move in that direction?
Yeah, definitely. We are, for example, working on flexible batteries, polymer-based batteries. There are electrolytes which are liquid electrolytes normally in our batteries, but one is working on solid electrolytes. They are much more safer. And if you use polymer electrolytes, with the polymer anode and cathode and so on and so forth, the batteries are much more lightweight. For example, we are working for batteries for drones applications in agriculture. Okay, you don't want the battery to be too heavy for carrying that drone and so on. So there are many battery systems, for example, wearables that you have.
I'm actually talking about the other direction, where we do not require a battery to be portable. Let's say I want to put a battery in my basement where I can store power, a large amount of power in.
Oh yeah, so for that, even now, people are using lead acid battery. Why? Because lead is recyclable. Almost 99.99% lead is now recycled. The only problem is people are now becoming conscious of the toxicity of lead. Okay, that's why they are trying to move to lithium or sodium batteries. And sodium batteries, for sodium is a bigger ion, and there are some other related issues about the weight of the battery. So that is why KPIT, who are interested in a bus, intracity bus, they went for sodium battery. If you want a two-wheeler, they are still going to lithium battery. Now, if you are saying in the basement, you generate a power source, there will be two options. There are fuel cell-based models, and there are batteries which are lead acid based, but you can go to even aluminum batteries, other types of batteries. So research is going on at least, let's say, 5 to 6 different battery chemistries. We are trying to follow that also. So there are options available.
Thank you. My second question pertains to what is on the screen. It has to do with sociology.
Yes.
I guess, because there is a cost towards any technology, like for example, even the solar panels. You mentioned that there is a cost of reclamation of materials or recycling of material.
Yes.
Often this cost is not passed on to the customer, and unless somebody pays for it, we are not going to be able to fund it. Is there any government policy or anything which goes into costing this?
Absolutely. Government has different, what is called as PLI schemes, which is called Production Linked Incentive, PLI schemes are available for battery making, for green hydrogen, and so on. There are also so those schemes, but the problem many people face is that for startups or small people who are in the innovation zone, they cannot avail these PLI schemes because they require a minimum amount to be put upfront for that, something like 1,000 crores or 2,000 crores, and only big companies and big players can avail these big schemes of government support. But there are other types of network projects that are government through MNRE and through DST, where if an industry and an academic organization are working together and industry shows interest and gives partial support, then government is putting something which is translatable to the industry which is in that domain. So those are the kinds of schemes available. But I think we have a long way to go to really succeed. Yeah.
I'm talking about the cost, the carbon cost, or what carbon emission cost, let us say. We talk about carbon footprint, but we never pay for the carbon footprint that we actually incur in the process of, let us say, traveling from here to Delhi. The ticket, my air ticket, does not have an excess cost for the carbon footprint that I generated. I'm talking about a sociological change, for example, a tax. I know it's not welcome in anybody's mind to pay additional tax, but it's a cost that we have to incur because we are causing that much mess and we need to clean it up.
Yeah, so now what is going to happen when the airlines are going to do all this, you will see now when if you have bought a ticket during the last year, there is also how much carbon CO2 is emitted by that flight. Now I have an Indigo ticket for 4th. It shows that this flight has so much CO2 emission and so on. So people are becoming conscious of it, and I'm sure today or tomorrow you and me will have to pay for it, because so far we had a free ride.
But Suresh, already in many countries for industry, carbon tax is already a reality.
Yes.
And people have already started thinking. Let me quickly go on to, we have another question at the back, but I wanted to bring up a question that from our online audience. We have about 50 people who watch this talk online today on our YouTube channel.
Yes.
And one of them has asked a question about plastic recycling, asking, are there any schemes to recycle plastics using natural resources like lightning and radiation from the sun, cosmic radiation, etc.? Are you aware?
So what people are trying to do is, as far as I know, the microbial intervention is very interesting in plastic processing, but people are trying to convert plastics into carbons also, but also that is not easily through renewable energy. It's still through battery grade materials, but the corresponding carbon footprint is not very satisfactory. So all these attempts are going on, and so far many of these wastes are put as landfills, okay, or you something else, but to the extent of the value added product and CO2 footprint, I don't think there are satisfactory answers or programs so far, at least to my limited understanding of the issues.
Thanks. There's a question there, which will be the last question today.
So,
thanks. Okay, you go ahead.
You said about this solar desalination.
You hold the microphone closer.
You have said about this solar desalination projects. Those were interesting, but I fear that they will make us learn to live with the global warming, in the sense that we are hitting the nature, and in response to that, because of the global warming, the weather patterns are affected, and some places are not getting enough rain. And by using this solar desalination, we are just making us able to survive without depending on the nature. So
without what?
Without depending on the nature's rainfall. So over the time, this makes us
this resource is not going to be equivalent to a rainfall. Okay, this is potable water. We need water for a variety of things. Okay, so for regions where they don't even have glass of clean water, this fog-derived water is important. Okay, cooking or drinking. It is not that for all needs it is like it will be equivalent to the rainfall and you are challenging nature to that extent. No, it won't happen like that, I think.
Yes, sir.
Thanks. There is a last question. Sorry.
Yeah. Yes. Yes.
Yes.
Yeah, hello sir. I want to know how sodium batteries, the dumping of sodium batteries are different than the lithium batteries. Like, is it?
Yeah, so it is the question of sodium is a bigger ion than lithium. Lithium is a smaller one. So luckily we have a material called graphite, all of you know, is a layered material, and the interlayer spacing in graphite is such that lithium can go happily inside and come out and get stored. It is a bulk storage. Okay, so lithium, when you charge, it goes inside and sits in layers of graphite. It forms LiC6 kind of bonding inside, 3 above, 3 below of the unit cell. Now, instead of sodium is a bigger ion and it doesn't fit there, meaning actually you have to calculate this as a transport. Okay, because suppose one lithium sits somewhere, the other lithium should be able to go inside. So this spacing between two graphene sheets of graphite is double the diameter of lithium. Okay, but if you take double the diameter of sodium, it doesn't go there. Some sodium may go here and stick there, so the other sodium cannot go. So for that, there is another form of carbon is required, which is called hard carbon. So we make that hard carbon by pyrolysis of, let us say, walnut shells. Okay, we have done that and we have a publication and a patent on that. So you have to make something where sodium can go inside and get stored. Okay, similarly, the sodium cathode, which are the sodium compounds from which sodium will come, they are different in character than the lithium compound. For example, lithium, I said LiCOO2. Right? In sodium, it could be something else, right? So those are the differences. Then there is a membrane, there is an electrolyte, and so on. So the battery construction, the elements are different, but technically, it is a bigger ion. The whole dynamics of storage and retrieval is different, but it is very interesting. And luckily, what happens is the hard carbon that we make, where there are spaces, more spaces inside, there is a fast charging. So sodium battery, I can charge in 10 minutes, for which lithium will take 30 minutes, like that. Okay, so those are kinds of different advantages and disadvantages, but sodium is in plenty, so lithium is very less, so we have to make choices for different applications.
Okay, but dumping wise, is it more eco-friendly or less?
No, lithium is, when you throw the battery, sodium is much more tolerant, we are in terms of ecosystem, than lithium. Lithium is a very foreign element. Sodium is a salt, right? So it is more friendly, but nonetheless, we will have to recycle everything eventually, I think. Yeah.
Thank you.
Thank you very much indeed, and thanks for this wonderful talk and interaction.
Thank you.
Let's express our gratitude, and thank you very much for the audience for turning up at the end of the year on a pretty busy week for everybody to come and listen to this talk. Please continue to come to our events here, and I thank Dr. Ogale for short notice coming in and giving a talk. Thank you very much. Thanks.